uniformly, right, throughout the incubator, so that all the eggs can receive what? Uniform heat. Got the idea? Okay? And not only that, each part of the eggs, each part of the eggs, every part of the eggs must receive, uniform heat. So what we can do? Let's say if you place the part on top, or let's say if you place the fan, so maybe at this side only what? Receive the heat, right now? So what we can do? There's a lot of answers. If let's say you place on a rack where the eggs will rotate. If let's say the egg rotated, it turn. What happened? If keep on turn, that means every part of the eggs is what? Can receive the uniform heat. That means they got a lot of answers actually over here. So if want to make sure that all the eggs receive uniform heat, okay, we need to place on a rack, and also if can the eggs what? Rotating. If not, what we can do is we place in a rack, okay, in a rack, and then we hang the rack. So let the rack to rotate. Let the rack to rotate. Also can also. So there's a lot of answers so that each eggs can receive uniform heat. And then one more is you want to maintain the temperature. So how you're going to maintain the temperature of the air in the incubator? How? What we can do? Okay, to maintain the temperature. One by one coming in. Wait. Okay, how you're going to maintain the temperature? So we can use what? We can use thermostat so that the temperature can be maintained. Yeah, temperature can be maintained. And not only that, you are going to, okay, the eggs normally will be hatched in about 21 days. Yes.
我上着课啊。
Hello? Chua Chong Yu. Okay. So what I stop, so the eggs are going to be hatched about 20 days. 20 days, actually 21 days, never mind, 20 days. So what we can do, you are going to open the incubator every day to check whether the eggs are already hatched or not? No. So what we can do, we can fix the timer. If you fix the timer, that means after 20 days, the alarm will trigger. Then you can open. No need to open frequently. So here, you want to you want to alert the people that it's already time's up, right? So what we can do, we can fix a timer. Okay, we can fix a timer. Okay, so these are some of the ideas. Yeah. So now I give you the answers. Take note in table. Okay, please take note. Number one. Point number one. Use. Sorry, not enough space. Use fan. Or you can write eggs rotate or eggs turn. When the egg keep on turn, also it can receive uniform heat. Eggs turn. Oh, one more. 7. No need. Eggs turn or hanging rack. Hanging rack also can. Hanging rack. Hanging rack. Hanging rack. Okay, hanging racks. Okay, why? Okay, we come up with the reason. Why? Okay, so the reason to ensure the eggs receive uniform heat. To ensure the eggs receive uniform heat. To ensure the eggs receive uniform heat. Okay, to ensure the eggs receive uniform heat. Okay, to ensure the eggs receive uniform heat. Okay, then we go for the next one. Second aspect, what we can do? We can fix here, fix or use thermostat. Thermostat, or we can use okay, you write this here. Thermistor. Thermistor. Use thermostat or thermistor. Use thermostat or thermistor. Okay, why? Why? Or you also can write, okay, you can write like this. Logic gate. Use logic gate. What is that? Logic gate. What is that? Wait, chapter 4, yeah, logic gate. Okay, use logic gate. Okay, why? Why thermostat? To adjust or to control temperature. Yes, to control temperature. Okay, to adjust temperature or to control temperature. Okay, to adjust temperature. Yes.
What is thermistor, sir? How it works?
Thermistor. Okay, you wait for chapter 4.
Okay.
Electronics.
Okay, sir.
Because the temperature. Okay, actually, thermistor is one of the electronic component. Okay, which will function according to the temperature. Where the temperature when increase, what happens is resistance of the thermistor will decrease. Okay, so it's vice versa on the other way. Yeah. So how it's working? When we come to the transistor as an automatic switch, that time you can see the thermistor, the sample thermistor, and how it's working. Okay. Now you take note first. Then when I come to chapter 4, I will tell you. Oh, please accept me. Who is this? Wait, someone is waiting. Oh. If let's say if you didn't see the message, you please send through me through the Telegram. Then I will accept you. Okay. So when I stop thermostat. Okay. Then okay. One more. Yeah. One more. The incubator over here. In between must be what? It can be vacuum. Correct. Okay. It can be vacuum, or what we can do is we can cover. Yeah. We can cover with. Okay. We can cover with insulator, so that we can reduce the heat loss to the surrounding. Okay, so we need to cover the incubator so that we can reduce the heat loss to the surrounding. So the next point is you write over here, use heat insulator. Use heat insulator. Okay, use heat insulator. Okay.
是这样子的吗？这不是我。
Okay. Okay. Use heat insulator. Vacuum wall. Vacuum wall, or okay, enough. Why? The reason, reduce heat loss. Reduce heat loss. Okay, reduce heat loss. Okay, reduce heat loss. And then next one is about the inner surface. Yeah? Inner surface. So the inner surface over here must be what? Must be shiny surface. The inner surface must be shiny surface. Why? Why it must be shiny surface? So that the heat can be what? Reflected. Correct? So the heat can be reflected. Yeah. So you write the next point is inner surface, shiny surface. Okay, please expect. Yeah. Inner surface is shiny surface, or mirror, or you can write mirror. Inner surface is shiny surface or mirror. Okay, why? So you write, okay, inner surface is mirror. The reason is can reflect heat. Can reflect heat. Okay, and then the next one is you write bulbs connected in, okay, or bulbs arranged, yeah. Bulbs connected also can. Bulbs connected in parallel. Okay, why bulbs connected in parallel? Why? So that heat can be supplied continuously. Heat can be supplied continuously. Okay, heat can be supplied continuously. Okay, heat can be supplied continuously. Okay, heat can be supplied continuously.
Sir,
Yes.
the mirror, right? We need to write shiny inner surface or need to give the example.
You write inner surface shiny, or just like mirror also can ready. Shiny surface, mirror. Okay.
Okay, sir. Thank
So
you.
that it can reflect what? Reflect heat. Yeah, reflect heat. Okay. Then we go for the next. Okay, the next one is what else we can write? Okay. 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 Next one is they also accept increase size of incubator. Okay, size of incubator. Okay, why? Can fill 200 eggs. Can fill 200 eggs. Can fill 200 eggs. Okay, can fill 200 eggs. Okay, I think one of the point I missed just now, I told you about the rack, right? Okay, a rack. Okay, for the rack, you write like this. The rack should be what do you say that? Multi-tiered rack. So you write like this. Multi, okay, tiered rack. I mean multi-level, yeah? Multi-level rack. Right? Okay. The reason is you write eggs are constantly to obtain heat evenly, to obtain heat evenly. Okay. Or to ensure all the eggs receive uniform heat. Also can to ensure all the eggs will receive uniform heat. You're right. All the eggs will receive uniform heat. All the eggs will receive uniform heat.
So,
yes.
Can repeat the reason for the expect increased size of incubator?
Oh, increase the size of incubator. Actually, the main reason is what we want to fill more eggs, right? More eggs, about 200 eggs. So you can write can fill 200 eggs. Can fill 200 eggs.
Thank you, sir.
Okay. Can fill 200 eggs. Okay. So that's all for this question. So I want to
So the last aspect,
which one? The last aspect, which one is it?
multi-tiered
rack.
means what, sir? How will be?
That means the layer. Multi-level, right? Multi-level. So that is, you are not going to put all the eggs together. So when you put in a rack, so that means what? There's in between, there's a gap. So that all the eggs can receive what? Uniform heat.
Oh, okay, sir. Okay, thank you.
Okay. So actually, this is something challenging. So that where you need to apply all the physics concept that you already learned. Okay, interesting actually question like this. Yeah, but nowadays they are already start to give all the points to the students. So easy for you. Okay, last time it's a bit challenging. So this one came out in SPM 2000, 2003. Sorry, 2003. SPM 2003. Long time ago. Okay, so that's all, That's all. Okay. Okay. Now we are going to continue with the DC motor, DC motor. Okay, I'm going to tell you something in the whiteboard. Before that, I look for one file. Oh, I already sent to the group. Yes, I know. Wait, where is it? DC motor. Yes, it is here. Wait, okay. Okay, so just for your knowledge, last week I explained to you about the turning effect. I'm not going to discuss about the turning effect today. Okay, we already spent a lot of time. And so what I did last week is I placed a magnet. It's a flat magnet. Okay, flat magnet. And then in between I place a coil. Okay, I place a coil, and then only I explain about the turning effect. Right? I explained to you about the turning effect. And then what I told you is the magnet that we are using is a flat magnet. The flat magnet is not suitable. It is not suitable. So what I told you, we have to use a curved magnet. It's just like curved magnet, so they give you a curved magnet or radial magnet. Okay? And then if you place a soft anchor in between, what happens? It will provide what? Radial magnetic field. Okay, it will provide radial magnetic field. Okay, so if you look at the components here, look at the components of the DC motor. I mean, a motor that use current, it using current, and then it will be what? It is going to be rotated. Okay, so here I use curved magnet. Okay, curved magnet. And then in between, I'm going to place a coil. Okay, curved magnet. And then in between, I place a coil. Okay, it is a coil. So let's say here is north, over here is what? South. North and south. And here, okay, last week we only go through this section, right? This section. But now we are going to go through another component is the external circuit. Here you can see like a arc split ring. Okay, arc split ring. Okay, our split ring. Yeah? Our split ring. It's a ring. Ring. Okay, ring is split into two. Cut. So become like C shape, right? Yeah. Our split ring and got name for this. This is what you call commutator. So it is very important. Commutator. Later you can add in the module, not now. Later. Commutator. We call this as a commutator. And then by the side, there's one more. It is dark color because it's made of carbon. This is a carbon brush. Sorry, carbon brush, which always will push. Yeah, will push the commutators. Will push, give a push. But it won't turn. Yeah, it won't turn. But the coil over here, it will be the coil over here is sealed over here, sealed with a commutator. Arc split. Okay, arc split ring. Yeah, and then by the side over here got spring. Okay, they won't ask anything about the spring over here. Don't worry. So spring. And then only we connect to a battery. Okay. So in this circuit, what we did, we already connect the coil with a commutator, carbon brush, and also to the battery. You want to increase the battery, or okay, you can use what increase current. You can add the rheostat if you want. You can adjust, or you can put anything that's going to be function. Okay. So here no need, leave it. And then if this coil, it is, let's say here is a metal rod, and this rod being gripped by this coil. The coil that you use over here, let it to grip the rod, metal rod at the center. So when the coil is being turned, what happens over here? Okay, let's say here is a wheel, okay, wheel of a toy car, or it can be a small fan. So when the coil is being turned, what happens? Coil turn, that means the fan or the wheel also will turn, right? Will turn. And then how about the wheel? It will turn, okay, it turn, rotation like this, and then turn back. Or it is rotating in the same direction. So if you look at the fan, the fan or the wire rotating in the same direction, right? It is rotating in the same direction. So that's one that we are going to go through. How to make sure that the coil over here rotate in one direction only, and what is happening over here? So when the coil turn, remember, coil turn, the fan turn, commutator also turn. Commutator turn, but the carbon brush won't turn. It's just give a push only. Give a push, that commutator turn, carbon brush still remain there. Okay, remain there. So that's all that we are going to study. So you can refer to notes. No, not. You already print out? You already print out or not?
Already, sir.
Yes.
Yeah, okay.
Yes, sir.
So you can take note. If not, you have to draw all these. Yeah. So we don't want to waste time. So let me share the screen. Okay. Actually, in this handout, I will give you three. This one you're going to study the next next subtopic. So subtopic 2 and 3 will take time. Okay, don't worry about syllabus. We got time. We can cover. Yeah. Okay, these two will take time. After that, yes, we can go very fast. Okay, so let's start with this. Check first. 0, 90, 90, 180, 270. Okay. So this is the diagram. So later, what you're going to do is you're going to label. Okay. You can label what is okay. Here got label, right? You need to know this name. Yeah? You must know this. Okay, you must know this. What is this? Commutator, you must know. Okay. And then carbon brush, not necessary. Yeah, not necessary. So you leave it. Okay. Shape, you see the shape of the magnet. It's a curved magnet. You know the reason. So that you can concentrate the magnetic field. And then in terms of number of turns of coil, what? Only one coil. If you increase the number of turns of coil, what happens? The force acting increase, the coil will rotate faster. If you want to make sure the coil rotate faster, you can use a strong magnet. You can increase the current. So these are the factors that will affect, okay, the speed of rotation of the coil. So later I tell you. After we finish this, then I tell you. Okay, now please label in this diagram, okay, the direction of the current. Okay, here is what? Positive, here negative. Okay, label first. Current flow in this direction, correct? Okay, so you look at the coil, current flow, this is the direction current flow. In the coil, over here, current flowing inward, right? Then come to the right hand side, current flow is what? Outward. Okay, so we label the current first. Okay, label. Okay, after that, please use the rules. Okay, let's say here, I give you a letter A, B, C, D. Okay, look at the side or arm AB. Okay, look at the arm AB. Okay, use Fleming's left-hand rule. Identify which direction the arm AB will be pushed. Which direction it will move, upward or downward? Check and see which side it will move.
Upwards.
Upward.
Upward. Yes, sir. All of you got it? It will move upward. Anyone else got problem? Tell me. No problem, right? Okay. So let's check current. Okay. Yes, on the left hand side, the force acting will be upward. So we label over here. We label over here with the arrow upward, right F. Okay. Confirm on the left hand side, right hand side, on the arm CD, the force acting downward. So what happened? The coil will rotate in clockwise direction. Correct? Clockwise direction. So please use the rules, Fleming's left-hand rule, to identify the direction of force acting, and also we check the direction of the current flow. Okay. Anyway, remember in this diagram, wait, I change color. Okay, the carbon brush, spring, the coil, battery, all these will remain over here. It won't move. Okay, it will remain there. Okay, now come to the first one. Come to the first one. Check first, anyone waiting or not? Yeah, Tarinish. Okay, so in this first diagram, let's say this is a 0 degree of rotation. Okay, this is what? 0 degree of rotation. So we write over here 0 degree. Okay, 0 degree of rotation. Smaller. Okay, 0 degree of rotation. Okay, let's identify the terminals. Yeah, terminals. Okay, terminals. I choose green color. Okay, here positive, negative. Oh, I choose a red color better. It's easy. Yeah. Okay. So positive, negative. Current flow. Okay, label the current flow. Label current flow. Okay, label the current flow. Current flow through the commutator, you can see here, I already differentiate with the color. The commutator with the red and also black color. Yeah. Okay, red and black. Actually, in the exam, you don't need to write with the two colors. There is no need. Here, I show you with different colors so that you can see every 90 degree of rotation, what happened to the coil and what happened to the current that flow in the coil. Okay, so current flow through the where is the pointer? Okay, current will flow. Right. Okay, over here, right? Okay, where is it? From A to B, yeah? Current flow A to B. Okay, you label over here current as what? I. Current as what? I. And then come to the, okay, current flow from A to B, come to what? C to D, correct? So now, current over here, C to D, you write over here, I. Okay, so over here, let's rewrite current flow. Okay, in the coil, yeah, we're talking about the coil. But you see on the left and right hand side, I'm not drawing the magnet. Magnet is not given, but we just give the poles only enough, because if I draw the magnet, it got more complicated. So the one. So you can see on the left and right, got north and south. So that means you must know there's a magnet, but it's not drawn. Yeah. Okay, current flow from where is it? Okay, A to B to C to D. Okay, first one. Current flow from A, B, C, D. Okay. Now we look at the arm A, B, and also C, D. Arm A, B, and also C, D. Okay. On arm A, B, force acting where? And then on arm C, D, force acting which direction? Okay, A, B. Force acting
Upward.
upward. Upward. Check and see. Use the Fleming step to do, all of you.
Upward.
Never mind, let others to check. Yeah. Thank you. Okay. A to B, the third finger, A to B. Use the Fleming step and rule. Yeah. Sorry. Yeah. Yeah, I can not show you. A to B. And then north to south. You can see your thumb will be pointing upward. Okay. The middle finger will follow inward, right? And then your pointer will be towards the south. And then you can see your thumb will be upward. Okay, this is your thumb. Force will be upward. So on the left hand side, the force acting is upward. So here we label with F. Force upward. Okay, now come to the arm CD. Arm CD, maybe you'll face problem, never mind. If you already identify on the left hand side AB, confirm on the right hand side, okay, on the arm CD, you can check if you want. So the force will be acting, where is it? It will be acting downward. Okay, so downward, and then what happened? The coil will rotate in clockwise direction. Okay, it will rotate in clockwise direction. So we write answer on arm AB, force acting upward. On arm CD, force acting downward. We go through a bit detail, yeah? A bit detail, so that you won't confuse with generator. That's the difference between the motor and also generators. Okay, and then the coil rotate in clockwise or anti-clockwise? It will rotate in clockwise direction. Okay, it will rotate in clockwise direction. I hope you can copy this in the notes that you already print out. Yeah, you just add only. Okay, so that you don't need to, they won't ask you to draw, but they can ask in terms of essay question. Essay question, I mean in terms of magnet, in terms of number of turns of coil, in terms of current, okay, and then the function of the commutator, additional features, can, all this can. Okay, so now the coil will rotate in the clockwise direction. So now when the coil turn and then rotate, come to 90 degree of rotation. Here's 0, over here is what? 90 degree of rotation. Okay, 90 degree. But you look at the terminal. Here, positive, negative. Okay, so current flow, correct? Current flow, look at the pointer. current flow. Oh, what happened? No connection, correct? No connection over here. So is it current flow? No, current is not flowing. Current is not flowing. Then what happened? The coil will stop, right? Yes or not?
No.
The coil won't stop. Why? Because in the first diagram, okay, this one, right? In the first diagram, the coil is being what? Rotating is in the clockwise direction. So when the coil become 90 degrees like this, although it is not in contact, but the coil will maintain its rotation due to what? Its inertia. So the inertia of the coil will make the coil to rotate continuously until this commutator in contact with the carbon brush on the right hand side. And then the black color commutator on the left hand side over here is in contact with the carbon brush on the left hand side. So once it touch, what happened? The current will start to flow. Okay. So the second one over here, no current flow in the coil. Okay, no current flow in the coil. Okay, no current flow in the coil. Okay. Then what we can write? No current flow in the coil. The coil. Oh, sorry, no current in the coil. Then no force acting. But the coil continue to rotate due to its inertia. Or you can write, there's no force acting on the arm AB and also CD. Where's the arm AB? Okay, I forgot to label this. Arm AB. AB here, A over here, B over here, C and D over here. But no force acting, but the coil continue to rotate due to its inertia. Okay, it will rotate due to its inertia. Okay, finish. Okay, so it continue to rotate due to its inertia. Okay. Okay, rotating in the clockwise direction. Yeah? Okay, now we go for the third. Okay, we come to the third. Yes, I want to check first whether you can see or not. Yeah, can see. Okay, we come to third. Yeah? Okay, first of all, let's relabel the terminals. Yeah, terminals of the coil. Okay, this color. Okay, where's the AB now? You can see the red color carbon brush, commutator comes to right. Okay, so the A over here and B over here. So A will be on the right hand side and B also on the right hand side, but you can see, right? Okay, you can see. So let's relabel. Label over here is A, B, C, D. And now 0 become 90 and this one become what? 180 degree of rotation. Okay, 180 degree of rotation. You can see the commutator. Commutator here is what? Red. Here is what? Black. But you see over here, left hand side is black, right hand side is what? Red. So that means the position is already changed. And then you see the coil, arm AB on the left hand side, but here arm B on the right hand side. Arm CD on the right hand side in the first diagram, but here on the left hand side. Okay, so let's check with this. Okay, let's draw the direction of the current. Positive, negative, current flow. Okay, current flow. Where? Okay, current flow from the positive terminal through the carbon brush, where I already colored it with the black color, through this commutator, coil, and then where is it? D to C, and then B to A, back to here. Correct? Complete. So current flow, okay, let's be label current flow I, and here is a current flow I. Okay, so let's be like we follow this. We follow the first one here. We follow this. Yeah. Okay. I need to enlarge a bit. Okay, so we write current flow from D to C to B to A. This is the direction of the current flow. And then let's check on arm AB, on arm CD. Okay. Identify the direction of force acting and then label. Label in the diagram. Please label in the diagram. Okay, identify the force. DC, where's the force acting?
Upward.
You're not drawing the diagram, I know, but you're just labeling only. When you label, so that you can see clearly what's happening. Okay, on arm AB, where is the force acting?
Downward, downward.
Downward. Only one answering. How about the others? Sleeping. Okay, later I'm going to call your name. Get ready. I'm going to call your name. Get ready, eh? Okay. AB, it is downward. So you write F. CD. Okay,
Upward.
CD.
Upward.
Upward. Okay, you just identify on one side, then on the other side will follow. Okay, so upward. So we write over here AB. Okay, force acting downward. You will see the almost same story as this when come to subtopic 3. Yeah. Okay, is downward, and then CD, force acting. Okay, force acting upward. Yeah. Force acting upward. Then wait, I'm going to call. Okay, who is it? Who want me to call? Okay. Camellia. Answer. Camellia. Saja Kelang Lama. Answer, please. Rotation. In which direction the coil will rotate? Camellia. Answer. Camellia, answer. Don't type in the chat box. The one. Answer. Turn on the mic and then answer. Camellia, are you here? Okay, answer. The coil rotate clockwise, anti-clockwise. Camellia, answer. I can't hear you. Hello? I know some. Hello, Camellia? Answer, please. Camellia, I looks like you're trying to say something, but no sound here. Okay. Wait. Alvin Tan.
Coil rotate in anti-clockwise direction.
Anti-clockwise. You see the arm DC upward.
Clockwise.
It is still what? It is still rotating in clockwise direction. Still same direction, yeah? It's not changed. It's not changed. So
Okay, sir.
okay, never mind. We observe carefully the diagram, yeah? So here, coil rotate in clockwise coil rotate in clockwise direction. Okay, the coil rotate in clockwise direction. Okay, So you can compare the first one and second one, first and the third. Okay, before that, let's continue with the last one. Okay, for the last one, it is, sorry, what? 180. Okay, first we label A will be here. Here, A, B, C, D. You can compare now. You can compare. You see over here, A, B over here. If it goes down, right, goes down. So here is A, B. And then C, D over here, it will comes upward. So here is what? C, D. Okay, C, D, yeah? Okay, then look at the terminals. Terminals. So here positive, negative. Then what happened? Current flow. Oh, what happened? No contact. Is it current flow? No. So no current flow. So what happened? When come to 270 degree of rotation, okay, 270 degree of rotation, what happened over here? What happened? No current flow in the coil, but the coil will continue to rotate due to its inertia. So they mean this one you have to copy. Same, sorry. Copy this. Copy. Same. Don't draw this, yeah? Okay. Over here the coil rotate in the clockwise. Gently, okay. The coil still what? Rotate in clockwise. So when the coil over here rotate, okay, continue to rotate. Okay, the arm CD will come to the right hand side. AB will go to left hand side. So don't draw this. Is it? It's same as this? Check and see. Is it same?
Yes.
Same. So they mean when come to 360 degree and also the 0 degree, so actually same. Okay, no change. Okay, no change. So anyway, in these two situations, the most important thing that you need to check over here is, okay, let's check one by one. I highlight first, yeah. Highlight first. Okay, I use blue color. Easy. Wait. Smaller bit. Okay, look at the current flow. Current flow from A, B, C, D. This is the direction of the current flow, correct? A, B, C, D, yeah? Current flow. Okay, and then look at the third diagram, under 80 degree. Current flow from DCBA. DCBA. You see, yeah? Current over here, where is it? On the left hand side, A to B. A to B. A to B. Over here, is it A to B? It's B to A. It's reverse. Here, A to B, C to D. But here, D to C, B to A. Okay? You see the current flow. You look at the current flow. Okay, current flow over here, DC. Oh, not clear. Current flow, DC. Hi. Okay, current flow from DCBA. Correct? Here, A, B, C, D. What happened to the current? current changing its direction, right? Current change its direction. Okay, but you see here, okay, A, B, C, D, here, D, C, B, A. So the question is, who change the current in the coil? Who change the current in the coil? Anyone?
Commutator.
Yes, your answer is correct. So answer is commutator. The commutator is the one that changed the current in the coil. Okay, for every 180 degree of rotation. So who change the current in the coil? Commutator. So you add over here in this diagram, please add commutator, the function. You must memorize this here. Change direction of current in the coil for every of rotation. Okay, change the direction of the current in the coil for every rotation. Okay, change the direction of current in the coil for every rotation. Okay, so what it costs when the current in the coil is changed? If not changed, if it is not changed, what happened? You can see the coil rotate clockwise, and then anti-clockwise, clockwise, anti-clockwise. So here, although current change in the coil, but the coil still rotate what? The coil still rotate in, you see, clockwise, one direction only, right? It's not reverse, yeah? It is not reverse. It's still what? One direction only. So, okay, you can add over here. Okay, one more function of the commutator is, okay, enable the coil to rotate in one direction only. Okay, enable the coil. Okay, you write enable the coil to rotate in one direction only. The coil is not rotating in anti-clockwise in this case. But if in the exam, maybe they can change the poles of the magnet or direction of the battery being connected. Yeah. So maybe the direction will be in anti-clockwise. You check everything in terms of the terminals of the battery. Okay, in terms of poles of the magnet, all these must check and then use the correct rules to identify the direction of the coil rotate, yeah, and also the current. Okay, so these are the two functions of the commutator. And then the carbon brush just to give a push, yeah, so that current from the external circuit flow in one direction. I mean, when the coil rotate, what happened? The coil rotate, but the battery and the external circuit, it won't rotate. Okay, it won't rotate. So it will remain there. Okay, so now we are going to continue with okay. You can add over here speed of a DC motor depends on. Okay, so when they ask about this experiment, still see. Experiment same as what we already discussed last week. So today I'm not going to discuss experiment, sorry. Same experiment. Remember the current and also the number of turns of coil, only. Current and also the strength of magnet. Yeah, strength of magnet. So here, number one, speed of a DC motor depends on number one. We write current. Okay, current. Okay, number two, we can go for current, number of turns of coil. Okay, but number of turns of coil, they won't ask you in terms of experiment. Yeah, number of turns of coils, so we use N. And then the third one is strength of magnet. That means the number of magnets, yeah, strength of magnet. So in this case, if any one of these increase, if all increase, what happen? Automatically speed increase. Or vice versa, yeah. So if any one of it increase, automatically the others also what? Will increase. I'm sorry, sir. Just now I already unmuted it, but I'm using laptop and lost my mic. Okay. Okay. Finished? Okay. Are you finished or not? So we continue.
Yes,
Okay.
sir. Yes, sir.
Okay. Stop presenting. Okay. Now all of you take out the module. Okay. Please take out the module. We are going to discuss. Okay. Take out one more. Later I tell you. Okay. Look at page 18. Wait, I check here my notes. Electromagnetism. Wait, okay, this one. Wait, I show you here. Screen sharing, start broadcast. Okay, please try this question. Please try this question. I give you 2 minutes. You can finish up this very fast. Try first. DC motor. Finish.
1 minute, sir.
Okay, wait. I'm waiting. Moving coil test generator. DC. Okay. Okay, so let's discuss. Yeah. Okay, diagram shows the structure of the DC current motor. Name the part labeled P and Q. P is what? P is commutator. Or you can write half split ring. Better write commutator. Commutator. Or you can write half split ring. Commutator or half split ring. And then Q is carbon brush. Q is carbon brush. And then what is the function of the part label P? Just now I already give you. P is what? Commutator. So change the current in the coil for every half rotation. Okay, change current in the coil for every half rotation. Or you also can write enable the coil to rotate in one direction only. So any one of these can be the answer. Change the current in the coil for every half rotation. Or enable the coil to rotate in one direction only. Okay, enable the coil to rotate in one direction only. Okay, the next one is Q. Q for what? Q. Just want to let the what? Let the current to flow, right? Okay, it give a push. It give a not give push. It enable the current from external circuit to flow into the coil. Enable current from external circuit to flow into the coil. Enable current from external circuit to flow into the coil. Enable current from external circuit to flow into the coil. Enable current from external circuit to flow into the coil. Okay. Next one is the state the direction of current flow in the coil. Okay. Current flow, where is it? I'll go be fast. Yeah? Current flow, positive, negative.
SVUT.
Yeah. This is the direction of current flow. So you're right. S to V to U to T. T. Okay. Then state and label the direction of the force acting on the arm SV. SV where SV is what? It is?
Upward.
Downward.
Yes, downward. Here
Downward.
upward. So here you write downward. Use the Fleming's second rule. Over here is what?
Upward.
Upward. And then name the rules used to determine the direction of the force acting. Fleming's.
Left hand rule.
Yes. Fleming's left hand rule. Okay. And then what is the direction of the rotation? It is anti-clockwise direction. Yes, anti-clockwise direction. Okay, it is anti-clockwise direction. Okay, it is rotating in anti-clockwise direction. Okay, the next one is what is the direction finish? State two ways to increase the speed of the motor. So two
Increase
answers what?
current.
Increase current.
Of coil.
Increase the strength of magnet.
Yeah, increase strength of magnet or increase number of turns of coils. Okay. Yeah. So increase or use stronger magnet. Use stronger magnet or use powerful magnet or increase number of turns of coils also can. Okay. Then next
Sir.
one. Yes.
Increase number of batteries.
Number of batteries, so increase current what?
Is it correct, sir?
Yeah, correct. If you're increasing, if you're increasing current, yes, it's not to say wrong, correct. But problem is what? Here you're using rheostat. Let's say if you still adjust the rheostat, you can maintain fix the current, right? But actually, it's not to say wrong can, but better you say current because we can use the rheostat to adjust the current. So better say current. Battery can increase number of battery, then you are increasing current, correct? Yeah. But better write current.
Thank you, sir.
Okay. Okay.
Sir,
So
increase
yes.
the number of turns of coil means how, sir?
Okay. It's like this. Increase number of turns of coils. Wait. Increase number of turns of coils. DC motor. Okay. Okay. Can you see this diagram? Okay. What we can do over here is, let's say, here got coil, only one coil, right? And then here is a metal rod where we'll connect to the external component. Let's say it's a fan or what, yeah? Okay. And then so here got one turn, correct? One turn. We grip the rod. Okay, one turn, then go for the second turn, fourth turn, and then more and more turns. Okay, here will be at more turns. Got it? Then only towards the end, the last one come over here. Got it? Increase number of turns. Of course, I mean every side of this coil, it will experience what? Force. So there will be a turning force on the coil where the turning force will increase. Okay, the turning force will increase. Okay, any other questions, Pastor?
Okay, sir. Thank you, sir.
Welcome. No more, eh? Okay, wait. Now I want to wait, where is it? DC motor principle. DC motor. Okay. Can you all see this? Can you all
Yes. I can
Yes, sir.
see.
Yes.
wait. Okay. Here is a simple DC motor. DC motor consists of coil with a commutator, arm split ring, where it's sealed over here. And then got magnet. Actually, the magnet is not suitable. It's a flat magnet, is not suitable. So we have to use what? We have to use a curved magnet or radial magnet. So reasons I already told you last week. Okay. So let's continue. When the current flow like this, okay, you see over here, current, here positive terminal. Okay. So positive terminal over here, current flow over here, current flow inward. So where's the force acting? The force acting will be upward. And then the force over here confirm will be downward. So the coil will rotate in clockwise direction. Okay, it will rotate in clockwise direction. So see what happened, huh? Okay, current flow.
Sir, no sound. You can't hear.
Sir, can't hear you.
Okay, sorry. Wait, I will show again. Now can? Okay. Can you now?
Can, sir.
Can.
There is
And
echo.
but echo, yeah.
Echo.
Okay, okay. See?
Echo, sir.
Now it's already touching the different surface. Yeah? Okay. You all look at another video clip. Okay, well, I wait. You look at the magnetic field and then the direction of rotation. Yeah, it will rotate at the same axis. Here positive, here negative. Okay, see current. Inward, outward. In, out. Okay, if you look at the coils over here, current all the while in the x-axis flowing in this direction, correct? Here, same direction. But current over here is inward, over here outward. But when the right hand side comes to the left hand side, it's not outward, it's inward. Because of the current in the commutator is what? Change. Commutator change the current in the coil. But the coil still what? Rotating in one direction only. So I want to stop here, yeah? Stop, enough. Don't waste time. Okay. Okay, so we already finished that part. Okay, now we continue with next one. Okay, here you can see, okay, the next one is moving coil meters, yeah, moving coil meters. So we go through in terms of animation. They won't ask you to explain detail, okay, how it's working, no. But they can ask you in terms of modification, yeah. Okay, I need to mute my purpose. What happened? Oh. Okay. Now you're going to go through moving coil meters. Moving coil meters means you can see if you are using ammeter. When the current flow, you can see the pointer will deflect. Okay, the pointer will deflect. When the current not flow, pointer will back to 0. When current flow, pointer deflect again. When more current flow, pointer will deflect more. Okay, so now we are going to go through this video clip, moving coil meters. Okay, you can see there's two curved magnets. Then center there is a soft iron core. There will be a force acting. That's the magnetic field. Combined with the magnetic field with current that flow in the coil will produce the turning effect. Then the pointer will deflect. But it cannot continuously rotate. Okay, it cannot continuously rotate. Why? Why it cannot continuously rotate? Because of there is a spring. You can see the red color spring. It will avoid. Yeah, there will be two springs. Okay, there will be two springs above and also below, which will control or which will control the coil from the continuous rotation. It won't rotate continuously. So it will give a counter force that the coil can back to its original position when the current is disconnected. Don't forget to subscribe. Okay, we go through one more. Okay, look at this. Another one.
Every craving satisfied at every price. Download the Foodpanda app and order now.
You can see all these in the YouTube.
Let us discuss Diacinval movement. The PMMC, or permanent magnet moving coil movement, is alternatively known as Diacinval movement, because this type of movement was invented by Diacinval. This system consists of a simple horseshoe-shaped permanent magnet. Two ends of the magnet are North Pole and South Pole respectively. These two magnetic poles create a uniform magnetic field between them. Between these two magnetic poles, there is a coil wound on a light metal frame. This light metal frame is so mounted that it can rotate freely in the field. Two phosphor bronze conductive springs are attached at upper and lower portion of the coil as control spring. One pointer is attached to the coil, as shown. As soon as there is a current in the coil, a deflecting torque TD is produced due to electromagnetic effect. The controlling torque TC is provided by two phosphor bronze conductive springs. The deflecting torque TD is directly proportional to current I through the coil. The controlling torque TC is directly proportional to deflection of the pointer theta. At equilibrium, torque TD equals to torque TC. Hence,
and one more is you see this.
Hello friends, welcome back to the channel Physics and Animation. Here in this video, we are going to talk about the working of permanent magnet moving coil galvanometer.
Galvanometer, there's a center zero galvanometer.
What is galvanometer? Galvanometers is an electromechanical instrument used for detecting and indicating an electric current. It is a sensitive electromagnetic device which can measure low currents even of the order of a few microamperes. Galvanometers works as an actuator by producing a rotary deflection in response to electric current flowing through a coil in a constant magnetic field. Now let's talk about the constructional detail of the permanent magnet moving coil galvanometer. Permanent magnet moving coil galvanometer is made up of a two concave permanent magnet, where magnetic field is directed from north to south, and rectangular coil that has many turns, usually made of thinly insulated or fine copper wire, is wounded on a metallic frame, which is pivoted from both the ends. The coil is free to rotate about a fixed axis. This whole arrangement consists of two phosphor bronze hair-like springs. The first one is connected to a upper pivoted free end of the coil, and second spring is connected to the bottom pivoted free end of the coil. And both of these springs are fixed from the other end by the help of a binding screw.
They wind the coil on a frame of aluminum.
A cylindrical soft iron core is symmetrically positioned inside the coil to improve the strength of the magnetic field and to make the field radial. There is a very important reason for keeping the magnetic field radial, which we will talk about later in this video during the working of a galvanometer. Also, the pointer is mounted on a pivoted coil for measuring the angular deflection in the coil, and two ends of the coil are connected to the two terminals of the galvanometer. Principle of permanent magnet moving coil galvanometer. Permanent magnet moving coil galvanometer works on the principle that current carrying coil placed in a magnetic field experiences a torque. When the current is allowed to pass through the coil, current starts flowing from A to B in the left arm of the coil, and from C to D in the right arm of the coil. As we can see in the animation, that in the arm AB, direction of the current is upward, and in the arm CD, direction of the current is downward, while the direction of magnetic field is from north to south for both the arm AB and BC. Therefore, according to the left-hand Fleming rule, two couple of forces or torque starts acting on a
See, the
coil,
spring also what? Being compressed.
which will help in rotating of a coil and causes angular deflection of the pointer. At this time, hairspring comes into play and creates counter torque to resist any extra unnecessary deflection or damage of a very sensitive pointer, and always ensures the proper functioning of the galvanometer. Corresponding calibrated scale is provided for converting the angular deflection of a pointer in a microamperes. Now let's try to understand that why this radial magnetic field is needed.
Radial magnetic field.
Here we have used concave shaped magnets to provide radial magnetic field. But why?
Concave magnet.
Let's explore it. As we all know, equation of the torque in this case is
Okay, this one only.
NIAB sin theta, where N represents number of turns, I is the current,
Okay, finish. So I hope you understand. Now straight away you come to the module. You come to the module. I need to check here. Today's the 10th. Okay, I need to check my Word file. Electromagnet. Where is it? Electromagnetism. Yes, 2019. Okay, turn to your module. They won't ask you to explain. Turn to your module. Come to page 14. Yeah, page 14. Okay, page 14. This one. So they didn't ask anything about the moving coil meters. Only once they asked, but there's no big question for the moving coil meters. But in the syllabus, it's already mentioned. So when you're talking about the moving coil meters, it can be ammeter, it can be galvanometer, it can be a wattmeter. So normally when you're using what you see, you only see what the pointer deflect. Deflect to left, deflect to right. Okay, when the current not flow, it back to zero. So actually, if you look at the components inside there's a coil, there's a spring, okay, and then there is a soft iron, okay, and then you look at the shape of the magnet. All these can become points for the essay questions. Yeah. So moving coil meters, it can be wattmeter, it can be ammeter, or it can be galvanometer. So now look at the aspects and also the modifications here. Parts and the functions. Okay, I want you to highlight the keywords only. Okay, first one. The shape of the magnet. Wait, I need to copy this. Shape of the magnet. Wait, Okay, if you look at the shape of the magnet, so here, curved magnet or concave magnet. Okay, or you can write radial magnet. So all these points important. You can see the magnet shape, radial magnet or curved magnet, or you can write concave magnet. Okay, then why? Provide radial magnetic field. Provide radial magnetic field, simple. Or you can write, concentrate field. But this is the best answer. To provide radial magnetic field. Okay, to provide radial magnetic field is the best answer. Okay. The next one is the coil. Okay. If you look at the coil, the coil is what? You look at the measure over here, this side. This one. It is a rectangular coil. It's not a circle. It's a rectangular coil. Why? Because along, okay, let's say here, along this side, there will be a uniform force acting. Yeah, force acting over here inward. Okay, this one's outward. Okay, so the coil over here must be rectangular coil. I mean, you are talking about this side, rectangular coil. Why? Because there will be a force on the left and also right. Okay, there will be force on the left and also right. I mean, there's a force acting about its axis is the correct answer. Where is it? To give a deflection about its axis. I mean, over here is inward. Over here is what? Outward. So this axis. So it will rotate. On the left hand side, inward. Right hand side is outward. So it will remain along this axis. Okay, it will remain over here. Okay, so it gives a deflection about its axis. Enough. Okay, then you can see the C. The C is what? Soft iron core. Okay, why we place a soft iron core? We wind the coil on a armature. You can see, sorry, aluminum frame. Here got an aluminum frame like this. Okay, there's aluminum frame. Then what we did, we will wind the coil on this frame. There will be coil. We wind on this aluminum frame, and this aluminum frame is very light, very light. So, okay. So soft iron core. Why we place a soft iron core? So best simple answer: easily magnetized and demagnetized. Simple answer. Easily magnetized and demagnetized. Okay, easily magnetized and demagnetized. Okay, then one more. Because when you last week, I think I told you about this. Okay, when we place curve magnet, sorry, this is a curve magnet, and then in between we place what? Soft iron core. Then we wind the coil on top of it, right? On top of it, yeah, the coil. Okay, so here north, over here south. So what happened? It will provide what? Radial magnetic field. So medan magnet jejarian. This one that I told you last week. So it will produce what? Radial magnetic field. Okay, so you can see it is radius. Yeah, radius. Where is it? Okay, from here to here. So this is radius. Provide radial magnetic field or produce radial magnetic field. Okay, produce radial magnetic field or provide radial magnetic field. Okay, so another one that you can write over here, underline, is provide radial magnetic field or uniform magnetic field. Okay, because of your using soft iron core and produce a radial magnetic field, if you look at the scales over here, you see the distance over here, equal, right? It must be equal. So if you are using the soft iron core, okay, if you are using this, right? Okay, if you are using this soft iron core, what happened? You can provide what? The distance between the scales over here will be uniform. So the next one is the scale will be linear with evenly spaced marking. That means the divisions, right? It is equally spaced, equal distance. If not, if you are not using the soft iron core, close further, close further. So the distance is not uniform. If you're not placing the soft iron core, it cannot produce a radial magnetic field, and the scales also not uniform. They won't teach this in school, They won't teach. Okay, finish. And then if you look at some of the emitters, there will be milliammeter, there will be microammeter. okay, there's just an ammeter. So if milliammeter or microammeter, it can measure what? A small value of current. So if you want to increase the sensitivity of the ammeter or wattmeter, what we can do is very simple. This component here, you got it. Sorry, this one, spring, air spring. This spring must be very thin spring, so that very small current flow, it can be deflected. So the spring can be turned easily. If let's say the spring is very stiff, it cannot be turned. Very difficult. So here, the spring over here must be air spring. Okay, air spring or control spring as well. Fine spring. Why? Why? Okay, you write this. Increase sensitivity. Air spring. It means a very small spring, fine spring. If you look at the galvanometer, wattmeter, ammeter, actually you can see the spring very small, but sometimes you cannot realize there's a spring inside. Very thin. Yeah. So thin spring or air spring. Okay. What force is spring? So one more answer. The best answer is this. It give or provide a counter force. Yeah. It give a counter force against the continuous rotation. If not, the coil will rotate in one direction only. Okay. So if not, the coil will rotate. But the coil won't rotate because of the spring will give a counter force from the continuous rotation. Okay, it will give counter force from the continuous rotation. Okay, it gives counter force. Okay, it gives a counter force from continuous rotation. Okay, and then the scale with a mirror. Okay, normally you can see there's a mirror strip over here. There's a mirror this side. It's a mirror. Okay, so mirror strip. Okay, you write this now to eliminate parallax error. To eliminate parallax error. Now, or to overcome the parallax error, to reduce a parallax error. To reduce parallax error. Okay, so that's all over here. We finish. Okay, this one normally they won't teach in school. Yeah, you can check. So I repeat again. Number one, yeah, number one is the magnet. Is the curved magnet. Why? Curved magnet produce a radial magnetic field. Simple, finish. We already go through this before. And second one is the coil. So rectangular coil. Why it must be rectangular coil? Number two, why it must be rectangular coil? So that it can give what? Force about its axis. It can give a force about its axis. Okay, it gives a force about its axis. And number three is a soft iron core. Why soft iron core? Easily magnetized and demagnetized. And one more is provide radial and uniform magnetic field. Actually, when you place a soft iron core, then only it will produce a radial magnetic field. But in exam, without soft iron core in between, if you the magnetic field will be like this side. So this one also what? If you write provide radial magnetic field, also they will accept. Actually, this one wrong. To concentrate the magnetic field. That's the correct answer. Okay, that's the correct answer. Okay, never mind. You write radial magnetic field, also they will accept. And then the air spring, increase sensitivity. Or you can write to give a counter force against the continuous rotation. Okay, to give a counter force against continuous rotation. Okay, give a counter force against continuous rotation. Okay, give a counter force against continuous rotation. Okay, then the last one is a scale with a mirror. Why there's a scale with a mirror? To avoid parallax error. The lightweight pointer, no need. Leave it. Okay. So that's all. And then I want you to take your time to answer these questions. Okay, answer these questions. All the theory questions you can start to answer. Okay. Now, number 2, 3, 4, 5. I will give you the answer. You can check. And then number 6, we are going to discuss. Not now. Number 7, 8. And then until 9, we will discuss. The rest, you can check on your own. Answers already given to you. Okay, answers already given. Okay, so now we still got another about 10 minutes. Okay, let's check. Okay, we start from here. Okay, on figure, you got any questions before we continue?
No.
No. Okay. On figure 1.1, sketch a magnetic field produced by 2 magnetoid magnets. So answer. So it's a flat magnet. It is a flat magnet. So how it looks like? So center, make it what? Straight. Here, at the end over here, let it to curve outward. Okay, let it to curve outward, and don't miss the arrow. That means it is not uniform. It is not uniform magnetic field. It is not uniform magnetic field. Okay, the next one is on the figure 1.2, sketch the magnetic field produced by the wire carrying current in the paper. So we draw. What happened? We draw curve or circles. So it is clockwise, anti-clockwise?
Clockwise.
It will be clockwise direction. Okay, draw. They can ask like this, the pattern. Yeah. Okay. Then come to the right hand side. On the figure 1.3, sketch a magnetic field produced by the wire carrying current into the paper. Okay. So first, we use the Fleming's certain rule to identify the force. Where is the force acting? Downward or upward?
Downward.
Oh, downward. Okay, good. So the force will be acting downward. So you put an arrow right F, and then what is the name given to the field that you have drawn? Oh, I mean here actually they ask you to draw the
Catapult field.
Yeah, actually they ask you to draw the field first, right? So what we did, we identify the force. Then only what easy for us to draw. So if the force is acting downward, so you draw the magnetic field, which is what goes upward more. Okay, there will be force acting upward. Where is it? Coagulant weighting. Okay. I think many of you missed today. Okay. And then one more below. Okay. Then next will be. Okay, the next one will be. There is a force acting on the wire. Draw the direction of the force given. Finish. Okay. So, C2, what's the field? Is what? The name
Catapult.
is? Yes, catapult field. Naming the field is a catapult field. And then state the 2 factors that affect the force acting on the wire. Answer?
Current and strength of magnet.
Yes, current and strength of magnet. Current and strength of magnet. Okay. This one also important because you can see in your textbook, they already give the diagram of this, but the question the way they said is very nice. Yeah, because there will be so many answers for that question. Okay. Question number 3. Figure 2 shows a steel wire. Don't let the class there. Wait. I need to talk. I need to say something about the upcoming classes. Yeah. Wait. Okay. Figure 2 shows a steel rod X and Y on a bare copper track. On figure, mark the direction of the current in the steel rod. Okay. Anyway, in this magnet, in this diagram, they already said north and south. But sometimes they won't give the north and south. They will ask you to label on your own. Then only they ask you to draw the direction of current. Then only they can ask you to identify the direction. So if you name the poles different way, let's see here given north bottom, south is above. But let's see if we label north above, south is below, then what happens? It will move in the opposite direction. Okay. So first step is mark the direction of the current in the steel rod. So where's the current in the steel rod? Okay, current. Okay, you see the positive terminal. Okay, current flow from here inward, right? So we draw current and then write I. Current I, and then the motion of the steel rod. Okay, use the correct rules. Use the correct rules. Where's the force acting? Left or right?
Right.
Right, huh? Okay, right. It is acting to the right. So we label with the F. Okay, we label with F. Okay. And then explain why the steel rod move in the direction. Okay. Actually, they ask you to explain, right? So to explain this, don't explain this. Very simple. You draw the fields. Okay, let's see here is what? South. Over here it is north. Assume that you're observing from here. Current is what? In. So we put cross. Force acting to the right. Why? Because of the magnetic field will be more to the left hand side. I mean, we can explain using what? Using diagram, but don't miss the direction of the magnetic field. So this one also what? Can represent the answer. So not necessary, you have to explain. Okay, you see, actually we know that with the current flowing in this conductor, what happens? There is a magnetic field, right? There's a magnetic field. And then there is a magnetic field from the permanent magnet. When these two magnetic field combine, it will produce a resultant magnetic field, right? So the current in the steel rod produces a magnetic field. This magnetic field combined with the magnetic field of the permanent magnet and produce a resultant catapult field. So this is the what you call catapult field, right? And then resultant force acting on steel rod. So you already draw and label the catapult field with the direction of force acting. So they mean the diagram over here can be the answer. So no need to explain using what? Sentence. No need. Just use drawing. Enough. Finish. Okay. The next one is state one way to reverse the direction of steel rod. So answer, how to reverse the direction? You want to let it to move in the opposite direction. I mean to the left. Answer. Only one.
Reverse the current.
Yes. Reverse current. Or, don't write both, yeah? Or, change the poles of magnet. Okay, change poles of magnet. Change current or change poles of magnet. Okay, anyone only here, don't write both, yeah? If you write both, reverse the current and change the poles, confirm your answer wrong. Why? Because the steel rod still moving in the same direction. Okay. Then, right. This is the answer for here, C. Sorry, answer for C, yeah? Not D. Okay. Right. Okay, now we go for the next. What will be observed if the steel rod replaced with aluminum? Okay, steel. Okay, steel and aluminum. Aluminum is what? Very light. It has what? Small mass. And some more, it has what? Low resistance. If low resistance, what happens? Current flow increase. Okay, current flow increases. Okay, battery low. Okay, current flow increase. So very simple. So if it is like small mass, what happens? If small mass, inertia is low, so the rod will move faster. So state and observe the steel rod replaced with aluminum rod. Answer is what? the rod move faster. Okay, the aluminum rod move faster. The aluminum rod move faster. The aluminum rod move faster. The reason? Okay, let's look at the reasons. Are we giving the answers? Highlight. Aluminum rod as what? Aluminum rod as low resistance and low density. So reason number one, reason number two. Okay, so if low resistance, low density, what happened? Larger current flow. Okay, larger current flow. Low resistance, larger current flow. Low density, what happened? Okay, if low density, this one you write lighter. Lighter. When lighter, what happened? Force acting is greater. Produce larger force. Produce larger force. When it produces larger force, what happened? Faster motion. Or move faster. Enough. Finish already. Finish. Okay. Okay, I hope you got the idea. So these are the keywords here. So remember, got 2 points over here: aluminum, lighter, and so low resistance. If lighter, small mass, so higher acceleration or move faster. And then low resistance, high current flow, force acting is what? Greater. Okay. Now, wait, I back to here. Okay, I hope you all can see me. Can see me or not?
No, sir.
No.
Can see the board, but not sir.
Can see.
Okay, never mind. I change the view. Now I can see.
Can.
Thanks, sir.
Okay. So I said, as I told you last time, we are going to continue until the end of this month, right? The class. So anyhow, I'm not confident that we can on our class by August, because the PKPP, right? They continue until August, and then according to what I heard from PPD, we need to maintain the distance 1 meter from body to body. So if I did like this, we cannot fit all the students in the class. We cannot fit all the students in the class, so we will face problem. I was so trying to arrange, if let's say we wait until the last week of July, then we can confirm, because what I heard, they are going to come and check in the tuition centers. If let's say it's crowded, then they will take action. Yeah, what I heard in kindergarten, they already go and check, and then they close the kindergarten and then open in September. So don't know what's going to happen. So we wait and see until end of July. We will know already whether we can start the class in tuition center or not, or we have to wait until September. Okay, so I will let you know third week or fourth week, the last week. Yeah, I will let you know. Okay, so that's all for today. So please do all the questions in the module. So then next week we discuss very fast, and we continue with the subtopic number 3, which is also very important. Yeah, after that all easy. Okay, thank you very much. See you.
Thank you, sir.
Thank you, sir.
Okay,
Thank you, sir.
Thank you, sir.